Hello, hello, and welcome to this video. In this video, we are going to study how to use mutexes to uh, synchronize data across multiple threads. So before starting anything or going with code, I want to draw your attention to something called the thread mutex, a man page, which will describe this. It is not a large man page, so we will go through it. Okay. So this man page describes pthread mutex init, pthread mutex lock, try lock, unlock, destroy. So a mutex can be statically initialized by fast mutex with pthread mutex initializer, recursive mutex with pthread recursive mutex initializer underscore np, error check mutex with error check mutex initializer underscore np. Now we have got five functions: pthread mutex init, which takes a mutex and mutex attribute. Then we have got lock, which takes a mutex, try lock, which also takes a mutex pointer. These are pointers. Then we have unlock and destroy. So the description we will read and then we will look at the code. A mutex is a mutual exclusion device and is useful for protecting shared data structures from concurrent modifications and implementing critical sections and monitors. A mutex has two possible states: unlocked, not owned by any thread, and locked, owned by one thread. A mutex can never be owned by two different threads simultaneously. A thread attempting to lock a mutex that is already locked by another thread is suspended until the owning thread unlocks the mutex first. Pthread mutex initializes the mutex object pointed to by mutex according to the mutex attributes specified in mutex attribute. If mutex attr is null, default attributes are used instead. The Linux threads implementation supports only one mutex attributes, the mutex kind, which is either fast recursive or error checking. The kind of mutex determines whether it can be locked again by a thread that already owns it. The default kind is fast. See pthread mutex attr underscore init for more information on mutex attributes. Variables of type pthread underscore mutex underscore t can also be initialized statically using the constants. So we have seen this. Pthread mutex locks the given index. If the mutex is currently unlocked, it becomes locked and owned by the calling thread. And pthread mutex lock returns immediately. If the mutex is already locked by another thread, pthread mutex lock suspends the calling thread until the mutex is unlocked. If the mutex is already locked by the calling thread, the behavior of pthread mutex lock depends on the kind of mutex. If the mutex is of the fast kind, the calling thread is suspended until the mutex is unlocked, thus effectively causing the calling thread to deadlock. If the mutex is of the error checking kind, pthread mutex lock returns immediately with the error code error deadlock. If the mutex is of the recursive kind, pthread mutex lock succeeds and returns immediately, recording the number of times the calling thread has locked the mutex. An equal number of pthread mutex unlock operations must be performed before the mutex returns to the unlocked state. Pthread mutex try lock behaves identically to pthread mutex lock, except that it does not block the calling thread if the mutex is already locked by another thread, or if by the calling thread in case of a fast mutex. Instead, pthread mutex try lock returns immediately with the error code tbusy. Pthread mutex unlock unlocks the given thread. The mutex is assumed to be locked and owned by the calling thread on entrance to pthread mutex unlock. The mutex is of the if the mutex is of the fast kind, pthread mutex unlocks always returns to its unlocked state. If it is of the recursive kind, it decrements the locking count of the mutex, number of pthread mutex lock operations performed on it by the calling thread. And only when this count reaches 0 is the mutex actually unlocked. On error checking and recursive mutexes, pthread mutex unlock actually checks at runtime that the mutex is locked on entrance and that it was locked by the same thread that is now calling pthread mutex unlock. If these conditions are not met, an error code is returned and the mutex remains unchanged. Fast mutexes perform no such checks, thus allowing a locked mutex to be unlocked by a thread other than its owner. This is non-portable behavior and must not be relied upon. Featured mutex destroyed the mutex subject, freeing the resources it might hold. The mutex must be unlocked on entrance. In the Linux threads implementation, no resources are associated with mutex subjects. Thus, featured mutex destroy actually does nothing except checking that the mutex is unlocked. Then we have cancellation information. None of the mutex functions is a cancellation point, not even featured mutex lock, in spite of the fact that it can suspend the thread for arbitrary durations. This way, the status of mutexes at cancellation points is predictable, allowing cancellations handlers to unlock precisely those mutexes that need to be unlocked before the thread stops executing. Consequently, threads using deferred cancellation should never hold a mutex for extended periods of time. The mutex functions are not async signal safe. What this means is that they should not be called from a signal handler. In particular, calling pthread mutex lock or pthread mutex unlock from a single handler may deadlock the calling thread. Pthread mutex unit always returns 0. The other mutex function returns 0 on success or and a non-zero error code on error. So we have several errors here. Pthread mutex lock function returns on the following code and error. E invalid value. The mutex has not been properly initialized. E deadlocked. The mutex is already locked by calling thread. Pthread mutex try lock returns E busy. The mutex could not be acquired because it was currently locked. E invalid value. The mutex has not been properly initialized. Unlock can return invalid value and E permission. The calling thread does not own the mutex. It is for error checking mutex only. Pthread mutex destroy function returns the following code and error. E busy. The mutex is currently locked. Now we will not go and look at pthread mutex attribute in it at this moment. We will look at mutex attributes later in probably when we discuss the attributes of the mutexes. So let's go back to code. Now this you already know error files and know about and error bot. We have already seen this in previous videos. So this is just an example of static mutex initialization. We have a structure my struct t or my struct tab, and we have a mutex t variable, pthread mutex t variable, which we have named mutex, and a value int. So this mutex can be used to protect this value. And how you can initialize this? You give it the value pthread underscore mutex underscore initializer, as we read in the man page, and value can be initialized to any value. So this is static initialization of mutex. Now the other way to initialize the mutex is dynamic. So this example, if you see, we have the structure tag, same mutex and value are there. We create a pointer to the structure and one status variable is there. We dynamically allocate the my struct t, and if memory location fails, it will be null, and we have problem allocating the structure. And then we call mutex init and we pass the mutex pointer, as you remember, and attributes are null here. So if status is not equal to 0, then we have problem initializing mutex. And finally, we destroy the mutex by setting the mutex pointer again. And if status is not equal to 0, we have problems destroying mutex. And finally, we free the data to avoid memory leak. Okay, although it is the last call in the function. So for this program, it is not mandatory to free the data, but it is generally good practice to couple a free call with the malloc. Now, what we are going to look at the main program is alarm mutex.c. So you remember our alarm program. Now we have that program extended to mutex. The alarm structure now contains the time t, time since the epoch in seconds for each alarm, so that they can be sorted. Storing the requested number of seconds would not be enough, since the alarm thread cannot tell how long it has been on the list. Okay, so we have alarm tag here, which is a pointer, or it will be basically an array or linked list kind of thing you can think of. It is not really linked list kind of thing, it will be an array. We have seconds here, we have time, and we have the message. So we initialize the mutex here, alarm mutex, okay, and alarm list is null, right? So you see that alarm mutex is declared outside the structure. It is not inside the structure. All right, and we'll see how we can use mutex to protect this alarm tag. Now, first we look at the alarm thread. So thread now contains alarm pointer, okay, and we have a sleep time, we have now, and we have status. So it runs indefinitely, looks for our processing commands. The alarm thread will be disintegrated when the process appears. So first thing we do is we take a lock on the alarm mutex, which we have declared here. Okay. And if status is not equal to 0, we say we have problem locking mutex. Next, what we do is we set alarm is equal to alarm list. So alarm list is null here, so we point the alarm to that alarm list. Okay. If alarm is null, we sleep for 1 second. This allows the main thread to run and read another command. If the list is not empty, remove the first item. Compute the number of seconds to wait. If the result is less than 0, then set the sleep time to 0. So we set alarm to alarm link. So if you look at link, it is here. So we read the one element from the list and we compute now. If alarm time is less than equal to now, then sleep time is equal to 0, else sleep time is equal to alarm time minus now. And we unlock the mutex before waiting so that the main thread can unlock it to insert a new alarm request. If the sleep time is 0, then call should yield, giving the main thread a chance to run if it has been readied by user input without delaying the message if there is no input. So here we unlock the message. So you see this alarm list is getting modified, okay, in this mutex lock and unlock. So that is the key aspect. That is what we are going to protect with mutex. And then if sleep time is greater than 0, we sleep for that much time, else we yield the CPU time. Now, if alarm is not equal to null, we print alarm seconds, alarm message, and we pre-alarm. So in the main message, we create the thread with the alarm thread and our arg is null. The usual error about and all is there. We print our message, we take the line and we process it. Now for alarm, we allocate an alarm. If alarm is null, we have a failure for alarm. We take the command and we free the alarm here. Okay. Now, if there is problem reading the commands, otherwise what we do, we take mutex lock on the alarm mutex and then we set alarm time is equal to time plus alarm seconds. Now we add this last to alarm list and next is pointer last. While next is null, next time greater than equal to alarm greater than time, alarm link is equal to next and pointer last is equal to alarm. So basically in the alarm link, we add this alarm at the end, okay? And then last is equal to ampersand next link and next is equal to next link. Now if next is null, last is equal to alarm, alarm link is equal to null. So this is the end of list. So we insert new alarm here. So this is basically a linked list behavior. And then we iterate over the alarm list and we continue till null. And finally, we print this statement where we print the next time, next message. And finally, we unlock the mutex so that the thread can process the alarm. Okay. So actual sleeping, if you see, is happening in the thread. This is the key item for our, where is that? Sleep. So So this is where the main sleeping is happening. Okay, so this is in the thread, and the main thread just modifies the alarm link structure. So I will share this code in a gist, and let's see, try to run this. So we compile gcc space mutex, not mutex, alarm mutex.c, and we run this, and we say we give it 5 seconds, and message is hello. So let's see what happens after 5 seconds. We should get the message back, and we got the message back. Okay, we can schedule another command, 5 hello, and then we can say 5 hello 1. So after 5 seconds, both should come back. And we have our alarm multi-thread messaging happening. So with this, I will end this video here, and I hope that you have enjoyed this video and found it useful. This code I will put in a gist, and the link of the code will be in description. So you can download it and run it to understand the code and go through it. If you have any questions, let me know in the comment box. So thanks a lot for watching the video. We will meet again after 4 days with more on multi-thread programming. So till then, I will say bye to you, and you have a nice day. Keep learning, stay curious, and most importantly, enjoy.